Okay, so um, hello everybody, and welcome to this couple of mini lectures. My name is Alf Martinez Felipe, and I'm going to start with a short lecture on hydrogen economies. I'm a chemical engineer lecturer at the University of Aberdeen in the School of Engineering, and I'm actually teaching in some of the masters that I'm showing here, like the Masters in Renewable Energies, Advanced Chemical Engineering Master, and Master in Decommissioning. So these slides are partly taken from some of the lectures we teach there, and obviously I will be very happy to take any sort of questions. I think it's probably best to do it at the end, but if you want to interrupt, I think you can still do it. So first question is, what is hydrogen economy? And eventually is a fancy term to explain that we can do a lot of things with hydrogen these days. And as in any energy network system, we're going to have different steps that we need to cover. So we're going to start with supply. So where do we take our energy source from? We're going to go through infrastructure that we need to get that energy source from point A to point B, for example, if we want to transport it, but also if we want to store the energy, because it will be the case that we may need it at some point later on after we have produced it. So storage is a very important part of the story, not only for hydrogen, but for in any type of energy system. And finally, and something we engineers tend to forget very easily is demand. So who's going to use that energy? What are the patterns for energy consumption? And this is going to be very, very important for us when we talk about renewable energies, because renewable energies have a very fluctuating mode, and obviously they change a lot with time and place. So in short, that hydrogen is an energy vector for us, which means that is something we can use to store energy and transport it to wherever we want to use it and whenever we want to use it. And coming back to the idea, and I'll show you obviously the benefits of using hydrogen respect to other energy vectors in this talk. But the main takeaway of this and any energy vector is the fact that we may want to use the energy at some other point in time when it is produced. And there are plenty of people working on this using very complex models. So in this slide here, in this part of the slide, you can see a classic diagram or a classic graph that shows the energy supplied or produced by renewable sources. And you can see that there is a certain pattern. It's periodic. Obviously, it repeats with the days and sometimes the months and the years, but it also has a lot of fluctuations. And for example, just taking solar, you can see that obviously you're going to have solar source of energy only during the daytime, and then the problem comes when, what happens if you need energy at some other time. So that's why we need to use these energy vectors, store the energy somehow, and then move it efficiently through places, and then use it where and when the demand takes place. But the other side of the coin, which is the demand part, is also complicated because people will use energy in different ways, in different manners, depending on where they are and when they are actually. And this is a plot, very simple plot of the household electricity demand in a house. You can imagine the peaks when people wake up and have the breakfast and the showers eventually. And it reminds me that my boiler is still broken, so I need to get this sorted out. And also when they come back for dinner, for example, or when they're probably watching TV. And those graphs and those models are really important to define our energy networks, how we prepare ourselves to provide this electricity or this energy when it is needed. So hydrogen, as I said before, is one of the many energy vectors that we can use, but it's actually quite beneficial, and we'll see later one of the reasons is because it's sustainable, and it can also be, it doesn't harm very much the environment, produces water when we burn it. But other important benefit is the fact that hydrogen is very light. It's actually the lightest element in the periodic table, which means that the hydrogen molecule, which is the form in which you'll find it in the gas form, is actually very small. and it carries a lot of energy per kilogram or per, let's say, mole. And this is, in this table here, you see the mass-specific energy density. This means that hydrogen, top of the table, is the champion of the world. This means that we can store a lot of energy. I can't remember what the units are for this table in particular, but you can see it can store a lot of energy per kilogram, and compared to any of the fuels that you have in this table. But unfortunately, you don't want to have a super big deposit of hydrogen in your car or in your house. And what matters in terms of storage of energy is actually the volume you can store. So the specific volume in terms of energy density is going to define our systems. And unfortunately, because hydrogen is a gas at atmospheric conditions, this will be the place where we will find hydrogen in this table. It's really low, it's there at the bottom. Even if we compress it to 700 bar, the amount of energy we can store per, let's say, volume is very, very small compared to other liquids or liquid fuels like diesel, gasoline, etc. And this is one of the things that we need to account for when we talk about the potential of hydrogen as an energy vector. And we'll talk about this later when we see infrastructure. But first, going back to my first slide, remember that we were talking about supply. So hydrogen can be obtained from very different sources. And the good news is it can be obtained from renewable sources as well, and with very little environmental impact, and we all want to do that. Mostly, almost every simple renewable source comes from the solar energy and is transformed into different stages and different sorts of energies, like, for example, heat or mechanical energy if we use tidal, or in this case, wind turbines. Dr. Dionisi will tell you a bit more in the next presentation on biomass. But from the hydrogen point of view, the interesting thing is that, you know, all these sources or all these processes end up having hydrogen as a result, among with other subproducts, of course. And now this is a way we can obtain hydrogen from renewable sources. Unfortunately, and you may be wondering why, you know, being such a fantastic energy vector, we don't have a society full of hydrogen cars already. Unfortunately, it is still quite expensive to get hydrogen from renewable sources, and most of the hydrogen that is already in the market comes from fossil fuels. Actually, it comes from steam methane reforming, which eventually is taking natural gas and producing some sort of reactions in which we obtain hydrogen molecules. Now, drawbacks of this: first, we're using fossil fuels, we're not using renewable energies, and second, we generate some CO2, and you know that means that we're gonna increase the global warming effect, etc., etc. So that's not ideal. And the hydrogen that is obtained in this way, it's called gray hydrogen because it comes from fossil fuels. We can eventually trap this CO2 produced in any other industrial application, and then if we capture the CO2 and we utilize the CO2 in another application, we turn our hydrogen from gray to blue. That's blue hydrogen, and blue hydrogen is already starting to be competitive in terms of cost. And if you manage to get hydrogen from renewable energy solely, which could be, for example, hydrolysis of water using, let's say, wind energy, then our blue and gray hydrogen turns into green hydrogen, and that's what we want. Now, unfortunately, again, the cost of electrolysis, and not only the technology, but also the cost of the electricity is still quite high. And this means that our numbers in this table are still higher than those from blue and green. But we're getting there, I think, and there is a lot of investment apart from projects, etc., going on. Now, the second part of this hydrogen economies diagram would be the infrastructure, and then we talk about the storage and transportation. So now we have our hydrogen, and we want to know what to do with it. And most likely, we're not going to use it at the same place we have generated, so we have to store it. And there are quite a few possibilities to do that. Here I just show a very simple separation between physical storage and chemical storage. In a physical storage process, we would simply keep our hydrogen molecule as it is, and we'll just try to either compress it to very high pressure, normally 700, for example, liquefy it at very low temperatures. We're talking about 77 Kelvin, which is minus 150 degrees, roughly speaking. So we still need energy to do that, or just getting into hybrid tanks that we'll see in the next slide. But we could also break down the hydrogen molecule. Remember when we had this bond between the two atoms, break down the hydrogen molecule, and then get the hydrogen atoms inserted in different molecules, which are bigger molecules and can form liquids. Now, the benefit of this is that a liquid is going to have a higher density, like gasoline or diesel, and then we can deal with transportation of liquids, which is going to be much easier than gases for safety reasons, but also for economics. You need to think that any step in between these states of hydrogen and transportation and energy conversion is going to take part of our efficiency out of the process. So we need to be, as straight as possible between supply and demand. So these are examples of the what we've called, let's say, physical storage. And here you see some examples of with numbers in terms of energy, density, volumetric. You see still very low compared to gasoline or other sources, but getting there. And the reason why I show these pictures is because one of the main aspects of hydrogen storage in the gas form is safety, and the fact that we cannot use normally materials that we would use for transporting gas or natural gas or typical gases. And that's because the reason is because hydrogen is very small, as we said before. It's a good thing for hydrogen density, but it can leak out dangerously and cause cracking on the pipelines and installations, and this is something that needs to be looked after very carefully. Now, alternatively, you can have it as a cryogenic hydrogen, so in a liquid form, but again, we need to apply high pressure and low temperatures, and you see the change in terms of density is not miles away. Something more innovative would be using hybrid hydrogen storage, in which we use like frameworks of porous materials with very small pores. This is obviously a very, very small scale. So these are molecules actually. So you can see that this is actually a sort of representation with our molecules of hydrogen trapped between these frameworks. Now again, this would be like a solid state storage, because these things are solid and then we can have it somewhere, but it requires some energy too. Now the other alternative, which is liquid-like chemical storage. In this case, we dissociate the hydrogen molecule, we break down the molecule into the hydrogen atoms, and then we place this hydrogen in a different molecule, for example, in ammonia, and then we can again create liquids with these hydrogen atoms inside these molecules, right? So roughly speaking, the idea is, remember that we can store hydrogen in this form, for example, in ammonia, but we want a way to reproduce the hydrogen, and this means that this process needs to be reversible. Very interesting graph here. When you show the volumetric density, which is what we want to optimize as a function of the gravimetric density. And just for reference, that would be compressed hydrogen storage at 700 bar. So in the gas form, that would be liquid hydrogen. And you see that these new hybrid systems are actually falling on the right side of this graph, which means that we can obtain very high volumetric densities. Now, the last part, almost the last part of this system is how we transport this hydrogen after it's been stored, and how we bring it to different places, and how we combine this supply with demand. And here you got some graphs and figures of projects going on in which people are trying to define the best way to combine, for example, the production of electricity using, in this case, wind turbines in the Orkney Islands, that then is used to promote water hydrolysis. So we would have this process there. And what we do then is to store hydrogen into, for example, those tanks that we saw in the previous slides, and bring it somewhere else where we can use it, for example, in fuel cells. So if you're interested on this type of projects, I can give you more insights. We're not going to spend more time because of the time we have allocated, but it's really interesting. For example, in Aberdeen, we work closely with companies that are decommissioning oil and gas platforms and use them to store the CO2 that is produced during steam natural gas reforming. So the idea is that the CO2 produced in these processes, when we obtain hydrogen from, for example, natural gas using water, that's in one of my previous slides, this CO2 that's going to come up after the CO, we can bring it to one of these decommissioned wells that are not used for extracting oil anymore, and then store CO2 and then get this fantastic blue hydrogen. And as I said before, once you got the hydrogen you produce in the system, you can get to transportation applications by using fuel cells, for example. And getting back to the transportation issue, there are quite a few projects trying to repurpose the grid, the gas grid, and use it as a hydrogen pipeline grid. But that is actually quite challenging because hydrogen, again, is quite light and this can cause problems. So SGN, which is the major distributor of natural gas in Scotland and in the south of England, they have a portfolio of projects in which they are trying to combine different materials, blend part of the system with hydrogen and natural gas. And most likely what's going to happen is that they're going to eventually create new pipelines used of polyethylene. But this is an ongoing process, and part of the problem, or part of the challenge here, is to actually generate a real and profitable demand for hydrogen. Meaning, at the moment, if you think about hydrogen, if someone tells you about hydrogen, you probably think about things exploding. And this is actually not fair, because within the safety procedures that they are installing is actually pretty safe. But trying to persuade the communities of the use of hydrogen is very important. Trying to create applications on the demand side, this demand side is very important. Changing the appliances, for example, at home, so that we can use hydrogen instead of gas is a reality. And this is, as I said before, something that's going on. There are a lot of cars, trucks, even trains fueled by fuel cells, which would use the hydrogen generated into transport applications. But again, we can use hydrogen as well to prepare new molecules. So, for example, ammonia that can be transported or used elsewhere, or fuels like gasoline or diesel, using some catalytic processes. So hydrogen is an energy vector, but it's also a very impressive feedstock for new materials. And I think Dr. Dionisi is going to talk a little bit more about that. So almost my last slide is just a reflection of what we've seen. I think in the future, we're going through a system in which we're going to be using hydrogen, but we're also going to use other sorts of energy vectors. And it will be a way of doing an intelligent and reliable way of distribution of energy, in which we can actually find sustainability. So it's probably during a few years when we will still have fossil fuels around, and the fossil fuels are going to let us have this energy transition. And in the meantime, we need to learn how to use the best energy vector and the best energy source for the best application. So I'm going to stop now before my voice disappears forever. Just reminding you that in Aberdeen, we do a lot of research on hydrogen, and we have a fantastic group of students working on a hydrogen fuel cell prototype. And you're most welcome to search us and do any questions now. And of course, I will be delighted to answer any questions later on.